steam in water plus vapor. Is it considered as a pure substance? If it's a mixture of ice and water, is it considered as a pure substance? Yes, yes. If you have only one, if you only have one chemical species, okay, can be more than one phase. Don't confuse if you only have one chemical component inside, we call this a pure substance. So different phases. So the different phases is a different concept. Okay. So any substance can exist in three phases: solid, liquid, and vapor. Or solid, liquid, and gas. Okay. Please remember, in some of my own tutorial groups, I have already highlighted this point. If you have two parameters, if you have two properties, but if these two properties are dependent each other, for example, if you have a pressure and temperature, these two are not considered as independent intensive properties. In that case, you cannot decide the state. So for example, if I just give you 1 atm, 100 degrees Celsius, what are the possibilities? Can you tell me? What are the possibilities? It may be totally water at 100 degrees. Is it possible? 100% liquid, or 100% vapor, or it's a mixture of liquid plus vapor. You have many possibilities. So it means the temperature and the pressure, they are dependent each other. Please write down. This is very important. So that's why you see the question normally, if we just give you a temperature and pressure, you cannot decide anything. So you need to know two independent intensive properties in order to decide the state. So for example, you have a temperature, then you have a specific volume. Or you have a pressure, you have a enthalpy, specific enthalpy. Or specific entropy. So anyway, if you have two independent, then you can decide. We will go to details later, what it means here. Okay? Now, let's see the diagram. Please, this part, I need your more attention from you. Okay? We mentioned for pure substance, here you have three important parameters. Pressure, volume, temperature. Okay? So for the diagram, normally we will have PV diagram, is temperature and volume. And we will have a PV diagram, is pressure and volume. So these are the most two commonly used ones. So I will explain in details. You need to know how to transfer the info from what you learn from steam table. You know already how to check the steam table, how to find the value you want, but how do you present on a diagram? What it means on a diagram. Okay? Alright, so on a diagram it's easier to tell actually. Okay? So please take note, if let's say you have this diagram, you have a temperature. Sit down please. For any diagram, labeling is very important. Okay, you need to know what you are plotting. All right. So you see here, the y-axis is temperature, the x-axis is a specific volume. Please take note the blue color curve. So the blue color curve is called saturation curve or saturation line. For any pure substance, if you plot, there will be a saturation line like this. Okay? So the saturation solution line will be split into two parts. Okay, so you can see here you have a maximum point. So the side and this side, any points on the line will refer to 100% liquid. Okay. The other side here, this side, any points on the line will be 100% vapor. Okay, so the substance will be separated into a few regions here. So if let's say it's from A to B, so A to B means haven't reached to the saturation point. So the B is just the saturation point. So any points at this area, okay, so means if you follow A changes into B, this area we call this compressed liquid. This is a new term to you. So any liquid below the saturation temperature, okay, so we call this compressed liquid. After reach to the saturation point, so you can see here, point B, what state? Can you tell me what state is point B? Just now I mentioned already. 100% liquid. Okay, 100% liquid. Then what is A to B? From A to B is still liquid. Okay, but we call that compressed liquid. Okay, alright. Then from B to C, so from B to C, you can see it's a horizontal line, right? So horizontal line means no changes in temperature. Example, you boil the water, you heat up the water, water is boiling, okay? So the water will change from liquid into vapor, right? Okay, so in that case will be a mixture of vapor plus water from B to C. But temperature will remain the same. Okay, and Q point C. C will be what? 100% vapor, yes. Okay, so you can see here. So we say B to C will be two-phase region. So from here, there will be a mixture here. How do we tell how much of the vapor inside? How do we call that? We'll come to that point later. For steam, we call that steam quality, right? Okay, you learned already. So if you want to know how much of the vapor inside the mixture, we call that steam quality, right? Okay, then from C to D, further increase. Please take note, you see the trend. The temperature increase from A to B. See here? Temperature increase from A to B, then B to C constant, C to D increase again. So because at point C is already 100% vapor, if you further increase the temperature, definitely will change to superheated. Okay, so this region will be superheated. Alright, so means superheated means the temperature of vapor is already higher than the saturation temperature. Okay? Here, so this is roughly how the TB diagram looks like. One more point. Please take note, it must be reasonable. If you plot anything, you must understand. You see from A to B, there's an increase of temperature, right? But you can see the volume, this is the specific volume from A to B, the volume change is not so much. Why? Because it's from compressed liquid, it's still liquid. For liquid, the changes is very small in specific volume. Okay? How do you tell? Later we can see from the steam table for the liquid volume, the changes is very small. Okay? But please take note. B to C, temperature is a constant. But because of the changes from liquid into vapor, right? So the volume will increase. Reasonable? Yes, right. Then from C to D, temperature further increases. So what will happen? Volume will increase. So it's reasonable. So the trend should be like this. Okay? Alright? But if let's say you plot under different pressure on the same diagram, how it looks like. Yeah. We call this ABCD isobar, means the pressure is constant. We also call this constant pressure line. Okay, so A to B, B to C, C to D is a constant pressure line. We call this isobar. Okay? Okay? So let's take a look of more complicated case. If let's say P1 here is 1 atm. Is 1 atm. Okay? Then now you have a higher pressure. For example, P2. I just give you an example, you will understand better. For example, P2 now is 5 atm. So you tell me 1 atm and 5 atm, which temperature is higher? Saturation temperature. 5, right? When you increase the pressure, the temperature will be higher. So it means the line should be in this trend. You see here, this one, P1, P2, P2 should be higher. Then if you have a 10 atm, further, so you have a P3, P3 should be higher than P2. Okay? Alright? So it means you will have a different isobars on the same diagram. So you can tell P3 should be higher than P2 should be higher than P1. Are you all following? The trend should be the same. Okay? Temperature increase. Volume should increase a bit. Then constant. Then increase further. Okay? But higher pressure should be above the lower pressure. Are you all following? Because the higher pressure means the saturation temperature should be higher. Okay? Another way for you all to understand, you can see here. You see the dotted line here we draw. So if let's say you do this. You draw a horizontal line here. This dotted line. Okay? No changes in temperature. Alright? But you have a pressure change here, right? So you have a P1, you have a P2. Okay? So you can read your V1 here, you can read your V2 here. Okay? So you can see here, which one is higher? V1 is higher than V2, right? Correct? So will P1 lower than P2? Yes, right. You can think, if you compress, the volume will be smaller, the pressure will be higher, right? But if you expand, pressure is lower, but volume will be higher, right? Correct? Then now you will understand why P1 is lower, P2 should be higher. Okay? You can compare in this way, you can also answer it. Are you all following? Yeah? Alright, now let's take a look at the details. Sorry. So just now we already explained, this region is for liquid, and this is a mixture of liquid plus vapor, and here will be superheated, and we also just now already mentioned, we call this saturated liquid line. At this side, the other side will be saturated vapor line, and we give a special name for the maximum point. We call this critical point. Critical point means at that particular point, you do not know it's liquid or gas or superheated. Okay? We call that critical point. So this is roughly how it looks like on a TV diagram. temperature volume diagram. Are you okay with this? Okay, summarize. Temperature increase, volume should increase. So it should be like that. Because temperature increase, you can imagine it will expand, right? Temperature increase. Okay? Then pressure increase means temperature increase as well. So higher pressure should be higher. Lower pressure should be lower. Now you are following? So this is for the first PV diagram. Now let's see another one. Okay? Don't confuse. If you understand, and I'm sure you will not be confused. Okay? So now it's a pressure volume diagram. Just quickly switch off. Now it's a pressure volume diagram. So now the y-axis is pressure, the x-axis will be volume. Okay, try to understand this. Just now we said for TV diagram, temperature increase, volume will increase, right? But now it's the reverse. Pressure decrease, volume should increase. Is it reasonable? Because expansion, the volume will increase, right? Okay, so please see the trend will be reverse, will be decrease. So the pressure will decrease with the increase of volume. Okay? And the same in the middle here, this region is still a constant. Just now we said, if it's a mixture of liquid and vapor, temperature should be constant, pressure should be constant. So this part must be horizontal. Okay? But only the trend from increase now should be decrease for pressure. Okay? Alright. Now you tell me, it's already here. T3, T2, T1, you can see here, T3 should be higher than T2, T2 should be higher than T1. So the same rule applies. Same rule, because higher pressure means higher saturation temperature, right? Lower pressure means lower saturation temperature. Okay? Alright? And another way for you is to compare, you see V2 and V3, you may compare the temperature of these two. You see, V3 is higher than V2, right? So it means T3 should be higher than T2. Reasonable. Heating will cause expansion. So volume should be higher. Okay? So this T should be higher, this T should be lower. Okay? But you need to keep in your mind, now we have these three lines decrease like that. We call this isotherm. So means temperature is constant. We call this. So means these lines here T2, T3, T2, T1. We call this constant temperature line. Okay, constant temperature line. So the rest will be the same. You still have a saturation line. You will still have 100% liquid, 100% vapor, and the mixture. Okay? All right? So this is roughly how the two diagrams looks like. Later we will have an example to practice a little bit. Where is your substance located on the diagram? Okay? Now let's see the phase change. Let's see the phase change. Do you remember in what cases there will be a phase change? Okay. Alright. So you have learned two types of heat. If you can recall, latent heat and sensible heat, right? For latent heat means there will be a phase change, but the temperature is constant. So which part is latent heat? If you go back here, can you tell me, if let's say you want to indicate from here, which part is latent heat? From here to here, the heat will be latent heat. Okay? But the sensible heat means either here, from here to somewhere, when the temperature increase, this is the pressure line. You should see the temperature line in here. So also this part, if there is a temperature increase, there will be sensible heat. We call that sensible heat. So means it involves phase change, but no temperature change. We call this latent heat. Usually, latent heat is very high compared with sensible heat. Alright? That's why in chemical industries, it's very common to supply steam as a heat resource to supply heat because the latent heat is very high. Okay? Then the sensible heat refers to in a single phase, but the temperature will increase. For example, the boiling process of water temperature will increase. A boiling process is a latent heat. If you want to heat up at the very beginning, it's still water, not changed to vapor yet. That part of heat is sensible heat. Until boiling happens, the vapor generated will be latent heat. Alright? So you have learned these few types of names. From solid to liquid, how do you call? From liquid to vapor, solid to vapor, vapor to liquid, and liquid to solid. Okay, so these are the names of enthalpy change. Okay, I think this one not very commonly encountered from solid to vapor. Some substances may have this, can change directly from solid to vapor. Okay. Alright, now let's see the phase diagram. The next will be a graph which will show you how solid, liquid, and gas, the phases can be displayed on one diagram. Okay, so any substances will have their own phase diagram. So for different substances, the phase diagram will look different. Okay. So now we will, generally, it will be like this. A typical phase diagram. Have you learned this in your PITC? No? Good. Okay. So a phase diagram, please take note of the two axes on the diagram. This is important. Okay. So this y-axis is pressure, then this is the temperature. See, we plot pressure against the temperature, and you see there are three lines here. There are three curves here, which separate the substances, solid, liquid, and gas. So means if it's on this line here, or this line here, or this line here, this will be a mixture of two phases. So for example here, this one, this line will be a mixture of solid and liquid. If beyond this range, so here, any part will be a solid. So here, anywhere will be a liquid. Then, if it's the borderline here, in between the two, this line will be a mixture of liquid and vapor. Okay? And lastly, will be this line will be a mixture of solid and gas. Okay? So the point where the three phases exist together, we call this triple point. Triple point. So any changes in between the phases, we have a name, right? Just now we said, maybe you call heat of melting, heat of freezing, heat of vaporization from liquid to gas. From gas to liquid, we call this heat of condensation. Okay? So these are the most commonly encountered. These two are not very commonly encountered. Alright? Okay? So this is a typical phase diagram. Alright? So if ask you to sketch a typical phase diagram, you should indicate there will be three curves. Roughly should be like this. the trend, okay? And then you will have a 3 region for the 3 states, okay? Now let's see how it looks like for water later. Oh, this one I explained already, okay? So this part I have already explained. Oh, one more thing is this. Here, increase in pressure usually favors the more dense solid phase. Is it reasonable? Okay, if you increase the pressure, density will be higher. Alright? Okay? And usually higher temperature are required to melt the solid phase at higher pressure. Is it reasonable? Yes, right? So if the density is much higher, definitely need higher temperature to melt. So this is something like this part. You see here, why the line is slightly like this? Because when the pressure increase, the temperature will increase here. Okay, for solid, I mean. Okay. All right. So this is one point I want to highlight. The rest I already explained. So any line there means 2 phases coexist. For the triple point means the 3 phases coexist. There's a critical point here. The critical point means beyond that point you cannot decide the phases already. It's not a pure either liquid or phase or gas. Okay. So some other points will be, you can see here, solid will be usually at a low temperature region. Alright. The gas normally will be at this side, will be a high temperature region, and the liquid will be in between. Okay. So you can see here the statement means this. Now let's see the. This is the phase diagram of water. Please take note. Water is a very special substance. Which part is special? Did you notice? Which part is special? Here, this line. Did you notice? Okay. For most of the substance, if the pressure increases, the temperature should be slightly increased. For just now we mentioned higher pressure solid need higher temperature to melt, right? Okay, but for ice is different. Ice is different. You see here. So this line is the reverse. For ice, between ice, solid, and liquid is like this line. Okay. So means when the pressure increase, slightly decrease of melting point. Alright? And also another point, I want to highlight the triple point for water is not 0 and 0. Maybe in your memory it's 0 and 0, it's not 0 and 0, you see here. So the triple point for water, the temperature is 0.001. It's not exactly 0. Okay? And the pressure is 0.006. Okay? Then where is the 1 atm? Normally, what you observe is under 1 atm, right? Here, 1 atm. So usually you can see a mixture between ice and water. So we'll be here. Okay? Alright. So this is a mixture. So this one is below 0.001. So what is the temperature? For 1 atm normally. Ice and water mixture. What's the temperature? Do you have any idea? No. You do a test today. Go back home. find some ice from fridge, mix with water and measure the temperature. 1 atm. What's the temperature? 0. Yes. So it's slightly lower than this. Okay, you see here? This is the temperature, right? Did you see? Okay, but if let's say now it's a mixture of liquid and vapor, where is it? Over here. So this line refers to the mixture of liquid and vapor, right? So you understand 1 atm for water boiling point is 100 degrees, right? So it's 100. Got it? Okay, So try to remember water is very special for this line, solid and liquid. When the pressure increase, actually the temperature is not increase, decrease. So it's a reverse. It tends to this side, it's not this side. Okay? Alright, so this is for water. Phase diagram. 0.01. Oh, yeah. Let me check. 0.01. Oh, yes. All right. Okay. All right. So the triple point means the three states coexist. Do remember, for water, it's not 0 and 0. It's 0.01 degrees Celsius and 0.006 atm. Okay. So you remember, if it's 1 atm for water and ice, will be 0, right? 0 degrees. Then the critical points for water is this temperature. Actually, there's a very special research area is to study for the critical liquid or critical substance. It's a very particular area. Beyond this point, what will happen? Okay? So you just need to know there's a point there. So this is for water phase diagram. Next. Let's move on. Next one will be the diagrams and tables, especially the steam table. This is not new to you, but there are a few terms I still need to highlight here. What are the terms? Do you have these few terms here? Okay? Now let's take a look one by one. Just now I said, if the temperature is below the saturation temperature, how do we call it? Actually, you have another name. If you compare the temperature, see here, so a substance cooled below its saturation temperature, we call this subcooled. Actually, subcooled and compressed liquid refers to almost the same thing, but it's on a different diagram. Because the subcooled is mainly referring to the temperature, right? So you compare the temperature with the saturation temperature. If lower than that, we call this subcooled. Okay, but if you compare the pressure, if the pressure is above its saturation temperature, we call this compressed liquid. You remember the temperature and pressure is the reverse. Okay, when the temperature decrease, the volume will decrease. But for the pressure is the volume, the pressure increase, the volume will decrease, right? So we will compress. So we call that compress. So this one is above, this one is below. Can you highlight? For temperature, should be below the saturation temperature. We call this subcooled. But for the pressure, should be above its saturation pressure. We call this compressed liquid. Okay? Then we also learned just now, we have a saturated liquid and saturated vapor. So which part is called saturated liquid? From the curve. Which part? Here. We come back here. So this part here, we call saturated liquid line. So means anywhere on this line here means it's 100% liquid. We call this saturated liquid. And anyone here at this side on the curve, we call this saturated vapor. Means 100% vapor. Okay? Yeah. So these are the few terms. Then for the superheated vapor means if the temperature is already higher than the saturation temperature, we call this superheated. Okay, another term which we already involved in your tutorial, another term is this, degree of superheat. Degree of superheat means the actual temperature of the superheated steam above or exceed the boiling point or the saturation temperature. For example, 1 atm, boiling point is 100. Now the vapor is 200. So what is the degree of superheat? 100. 200 minus 100. So that is called degree of superheat. Okay? So if now the temperature is 350, so you use 350 minus 100, the degree of superheat will be 250. Okay? So this is called degree of superheat. Then for you have learned a lot. If you see a mixture of liquid and vapor, you have to know what is a steam quality, right? So what is the meaning of steam quality? Although some of you use a lot already, but you still don't know how to write in words, how to describe. Okay? The percentage of steam means dry vapor. Please get used to the term. If we say dry vapor means 100% vapor. So how much of this vapor inside a mixture? So the percentage refers to the steam quality. Okay? So once you know the steam quality, so means you can calculate any parameters for the mixture already. So you can calculate volume, enthalpy, internal energy, and entropy. Please also take note of the symbols we commonly use. You can use either one. So in some of the steam table may be indicated as Hg, right? Some is Hv, right? Okay, for liquid will be Hf or L. Okay? Okay? Please, for these few formulas will not be given to you. By right, this is the definition. Definition means, listen, you need to memorize. Okay, see how much here is vapor, so means vapor times x plus the rest. 1 minus x will be the liquid, then times the liquid. So the same for all the parameters. So you just need to memorize one. Okay, x times vapor plus 1 minus x times that for liquid. Okay? Okay. So just now I already mentioned, if let's say both pressure and temperature are given to you, but they are dependent on each other, you cannot decide the states. So these two parameters All these two intensive properties are not sufficient to decide the state. So you need something else. So for example, if let's say water at 100 degrees Celsius and 1 bar or 1 atm, okay,